You all, in this video session we will see what is the Galerkian approach for 1D heat conduction. Okay, let's get started. The Galerkian approach of 1D heat conduction. We already know that Galerkian approach, it is an approximation method. Here we are assuming a displacement function, and the displacement function is put into the differential equation of the heat conduction. In our first video of this module, we derived the governing differential equation. You can refer the video, that is the first video of the module 4. Here d by dx k into dt by dx plus q equal to 0, where q is the heat generated, k is the thermal conductivity, and dt by dx it is the thermal gradient with respect to the length. In the Galerkian approach method, we integrate the differential equation and we assume the displacement function. This displacement function, here there is assumption of displacement function, it is the weighting function, and the differential equation, it is the residual function. Okay, the integration of weighting function, residual function over the length of the body is equal to 0. This is the Galerkian's method. You already seen this one in the first module itself. Okay, for this derivation, let us assume the weighting function are the shape functions. As in deriving the shape function, we assume the linear function, that is t equal to a0 plus a1x. Okay, so this is the assumption. Okay, after assuming and solving this one, we get the shape function. So let us assume the shape functions are the weighting functions, and the residual, it is the differential equation, that is the governing differential equation of the heat conduction. Okay, so let us integrate this with respect to x, that is equal to 0. Okay, we have assumed the function, that is shape function, and the residual function or the differential equation, that is d by dx into k dt by dx plus q equal to 0. Okay, you already know how to solve the shape functions or how to figure out the shape functions. Okay, let us assume t equal to a0 plus a1x. At node 1 temperature is T1, at node 2 temperature is T2. Okay, it is at a length of x equal to 0, it is at a length of x equal to L. Okay, solving this, we will get n1 equal to 1 minus x by L, n2 is x by L. Okay, these are the shape function in terms of local coordinates. Okay, this is the assumed linear function, and applying the boundary condition, that is temperature at node 1 it is T1 at x equal to 0, and at x equal to L temperature is T2. So applying the first boundary condition, we have T1 and the x value it is 0, and similarly at node 2 temperature is T2 and x value it is L. Okay, substituting the x values, we have substituting x equal to 0 at node 1, so 0 into a1 it is 0, so a1 equal to T1. Similarly, applying the second boundary condition, T2 equal to a0 plus a1L. Okay, already we know the a0 value, substitute a0 value, so it is T2 equal to T1 plus a1L. So a1 equal to T2 minus T1 by L. Okay, now we have a0 and a1. a0 is equal to T1 and a1 is T2 minus T1 by L. Let us substitute these constant values in the assumed polynomial equation. Okay, where a0 is T1 and a1 is T2 minus T1 by L. Okay, simplifying this, okay, let's see what are the coefficient of T1, that is 1 minus x by L, and the coefficient of T2, that is x by L. So we know that temperature at any point can be defined as shape functions and the nodal temperatures. So n1 T1 plus n2 T2. So the coefficient of T1, that is considered as shape function 1. The coefficient of T2, that is considered as the n2, that is x by L. So these are the shape function. It is in terms of local coordinates. Okay, now by the Galerkian's method we are finding the Galerkian's method. Okay, here weighting functions are the shape functions n1 and n2, and residual function, it is the differential equation. Okay, if it is integrated with respect to 0, let us see what we will get. Okay, weighting function into residual function over x length equal to 0, where w is the shape functions, and r value it is substituted here, that is kd. Okay, it is the same, d by dx k dt by dx plus q equal to 0. It is written as k into d square dt by dx square plus q equal to 0. Okay, substituting this r value, that is the governing differential equation. Next, now it is taken two terms, w into k d square t by dx square plus w q dx equal to 0. Okay, here by integration by parts method, it is integrated by the parts method, where w it is the u and v is k d square t by dx square into dx. Okay, you already know how to integrate or the product of two parts. Okay, you first keep the first part, that is w as it is, and then integrate v dx, integrate v with respect to x, that is k dt by dx, k dt by dx, then minus again integration of this part. Okay, what is the integration of this part? Okay, it is kept said integration of k dt by dx, and du by dx. So the u is w, so it is dw by dx into dx. Okay, now okay, it is simplified here. Okay, now we have this part. Okay, taking the minus in other side, we will have integration of k dw by dx dt by dx into dx equal to wk dt by dx plus integration of wq dx. Okay, here let us find what is dt by dx and dw by dx. Okay, we have just substituted the r value, that is the differential equation, and w value, that is the weighting function. It is not yet substituted. After substituting the differential equation, it is simplified. Now it has two parts. Okay, with the heat generation and with the differential terms. As it has two terms, w and this part, integrated by the parts. Why it is not taken two parts, where q it is the constant here. Okay, it is w is not constant, and this k d square dt by dx square, it is the dependent values, so it is considered as separate components. So by UV method it is integrated. So now we have three values. This value it is taken left side and the other two values on the right side, so we have the three terms. Okay, let us find what are the dt by dx and dw by dx, and substituting all the values here, and we will see what you will get in the next video. Okay, thank you very much.